Okay, hi guys, good morning. Became a little late. So we'll start right away. Let me share my screen. Okay. Right. So yes, so we have completed your chapter. That is, you have completed thermodynamics yesterday, right? So is there any questions you want to ask me, people, like about that particular chapter? Right? Any doubts which you went through? Did you do some problems or any other? We have completed 3 chapters. Is there any questions you want to ask? Right. Okay, so I suppose there are no doubts, right? So we'll move on. So I told you that I'll be teaching you hydrocarbons. That's the next chapter, right? Fine. So we'll start. Okay, right. Fine. So from the name itself, I can understand that we are going to study about organic compounds which contains only carbon and hydrogen, right? But guys, like what I thought is we will do organic as a whole. That's what I thought, like starting from hydrocarbons ending with amines, like in between I have alkyl halides, aryl halides, alcohol ethers, phenols, carboxylic acids, aldehydes, ketones, like all these things. I thought I'll just club them together and I'll teach you. That's the whole organic part, but we'll see how it works. Okay, right, fine. So in this itself you'll be covering most of the reactions, right? Most of the reactions you will be actually like completing here, right? But still, like, we'll see what happens, right? So anyways, fine guys. Now we know that we see it's in a way when it comes to organic, like you studied the first part that didn't involve any reaction. We just studied general organic chemistry, right? So we studied about reactive intermediates, we studied about resonance, we studied about the stabilities of carbocations, carbanions, right? Isomerism, right? So all these things now has to be applied in your organic reactions. That's what we are moving on, right? Okay, like I would say, I will not call this chapter as particularly hydrocarbons. Like I'll give you a overall idea, right? And then about all types of reaction which can happen in organic chemistry, right? Then we'll go for specific reactions. Is that okay? Right. Fine, guys. So under the types of organic reactions, I have the first type, right? So I have the first type of organic reactions. Right, I will just call them free radical substitution. Okay, so from the name itself you can understand, right, what is going to happen there. I'm going to have a free radical substituting another free radical. We know what is a radical, a single unpaired electron. If I have in the valence shell, those kind of species are what are called as radicals, free radicals, right? So one famous example I can tell you, that is when I go for say I have CH3, CH3 in the presence of light, I just write H nu, and sorry, yeah, sorry, Cl2 also I have to put Cl2 in the presence of H nu, chlorine in the presence of H nu, and I know what is going to happen, right? We know this reaction, right? So I'm going to have one of the hydrogen atoms getting replaced by a chlorine atom, right? So you will see that what happened. Right. Yeah, there is something happening, guys. Okay, right. So I will have this reaction happening, right? One of the hydrogen atoms is getting replaced by a chlorine atom, right? So not only for this guy, this is one of the substituents. I can even have something like this. Okay, so something like this means like I have CH3, CH double bond, CH2, right? So now there is something called as NBS. Okay, so NBS is ion bromosuccinamide. Okay, so I can, like, okay, if you want to write it, it is N bromosuccinamide, right? So you don't have to worry about the structure of N-bromosuccinamide, but you have to worry about what it does, right? So here I'm going to have allylic substitution, right? So what do you mean by an allylic substitution, people? Like, we know this is an we know what is an allyl carbocation, isn't it? So allyl carbocation will look like this, right? So whenever I say an allyl group, this is what is an allyl group, right? I have a double bond, then a single bond, right? So that is what is called as an allyl group, right? So when I say allylic bromine substitution, right, this is allylic substitution of bromine. So what is going to happen here is I'm going to have, say, this is the allyl position, right? So this is the double bond and this is the allyl position. So you will see that I'm going to have CH2 uh, Br, and this is going to stay. Right, so all these are going to be free radical substituents. So again, you can see that here I'm going to get the Br dot, right, and I'm going to have allylic substitution happening, right? So guys, we'll just see the mechanics. See, it's not about knowing the reactions alone, right? You have to know how do you go about the mechanism so that you'll be able to predict the products properly. Okay, fine. So these two are a few examples of free radical substitution, right? So we'll just see the mechanism. I think the first mechanism you should have known, I guess, like it's pretty simple, right? Fine. So we'll just move on. We'll just go for the mechanism, right? So we'll just take the first reaction. First reaction is this, that is CH3 giving CH3 CH2Cl, right? So for any free radical substitution, people, now I can give you one more example, right? So another example I can give you for free radical substitution is is this, right? So when I go for anti-Markovnikov's addition, right? Hope you guys, I'm using so many terms, assuming that you know certain things in organic chemistry. If you don't know, please stop me right there and ask. Okay, right, fine. So when I go for anti-Markovnikov's addition of water, right? So now there you will see that when I have right, so when I have CH3 CH double bond CH2, when I go for HBr in the presence of peroxide H2O2, we know what is going to happen, right? So here it is going to be anti-Markovnikov's addition of the, when you use a normal HBr, like the mechanism is different, but when you use HBr in the presence of peroxide, right, so there the reaction is going to be different. Like I'm going to get anti-Markovnikov's product in the sense that I am going to have the bromine atom substituted in this carbon atom, right? So you will see that I'm going to have CH3 CH CH2 Br, right? So this would have been happening, right? In all the reactions which I have mentioned, people, right? Free radicals are actually going to be the intermediates. Okay, right? So fine. So we'll just spend some time on understanding the mechanisms of all these reactions, all these three reactions which I saw now, right? Fine. So for the first reaction, that is the normal hydrocarbon free radical substitution, like this one, right? So I'm sorry, Br is not included. So the first one, right? So we'll see what happens there, right? So when I look at the mechanism, I have three steps. In any free radical mechanism, actually, there's going to be three steps. Understand that, okay? Right? So the first step, right, is what is called as chain initiation step. So in chain initiation step, first of all, you can see that right. So in chain initiation step, what happens is the chlorine atom, which is here, the chlorine molecule, which is here, it is going to undergo homolytic cleavage to form chlorine radical. Like that's what is going to happen. So you will see that in the initiation step, right, this chlorine, I'm going to have the light coming, right? So that is going to produce two chlorine dots, right? Two chlorine radicals is going to get produced. Okay, right. Now that's the first step. In the second step is what is called as chain propagation step. Right. So in chain propagation step, what happens is when I have this CH3, CH3, now in the presence of a chlorine radical, right, what is going to happen is I'm going to produce an alkyl radical in the sense that I'm going to have the alkyl radical produced, and obviously you would have abstracted a H dot from this, and that is going to combine with Cl dot to produce HCl, and this is going to keep on happening. More and more amount of radicals will be keeping on produced, right? Okay, now in the last step, that is the chain termination step, right? So you saw that I'm going to have one alkyl radical form. There is one more chlorine radical left. Now they will come together. Oops, sorry, this is nothing. So I'll have CH3, CH2 dot plus Cl dot combining together to form CH3, CH2, and Cl. Like this would have been the total mechanism. So you can understand, right? There is going to be a free radical which is getting formed, and that's the intermediate in this reaction, right? Okay. So now talking more about this reaction, guys, right? So instead of chlorine, right, if I use bromine instead of Cl2, if I use Br2, now that you understand that I'm going to have a free radical as the intermediates in this particular reaction, right? So if I ask you this question, oops, okay. If I ask you this question, say if I have something like this, say CH3, right? Say if I'll put two things, I mean, I'll go for two reactions. One is Br2 in the presence of H nu, and say this one is Cl2 in the presence of H nu, right? If I take these reactions, right? Fine. So we'll see what happens there, right? So you understand, guys. You tell me, say if I go for carbon numbers 1, 2, and 3, right? Now, where do you think is the most probable site for substitution? 1 or 2 or 3?
2.
Okay. Fine. We understand why is it like that, because obviously now it is going to depend on the stability of the free radical, isn't it? So in this case, say if at all you are going to have the chlorine atom substituted here in the third carbon atom or in the first carbon atom for that matter, right? So what you will be getting as a primary free radical here or here, we know it's going to be a primary free radical, right? But if this is going to get substituted here, right, here I'm going to have a secondary free radical getting formed, right? Obviously we know secondary free radicals are more stable than primary free radicals, so we expect that in both the cases chlorine or bromine should get substituted only in this second position, right? Because the stability of the free radical is as such, right? Okay. So what happens here is, now if I look at the products, right, if I really look at the products, what happens is I will be getting CH3, CH2, Br plus, oh sorry, it's actually CHBr, right? CH3 plus both the products will write CH3, CH2, CH2, Br, right? So these two are the possible products. Same goes here also, right? But when you look at the percentages here, right? So it's not like this is not going to get formed at all, but the major product is going to be this, right? I would say that, say this is 70%, right? This is 30%, right? Okay. Now, if I look at the case with chlorine, right? If I look at the case with chlorine, we'll see what happens there. So same amount of products, right? So no, not same amount of products, same type of products, right? So you will see that I can have one, two, one, two, three. Okay, this is not there. Okay, say here I can have your chlorine, or say the other product would be here I can have chlorine, right? So here, if you look at the composition, guys, the composition here is going to be 50-50. Right now, why is it happening like this is the question, right? So if I put bromine, I am getting what I'm expecting, that is the major product is accordingly a secondary free radical, and accordingly the product is also okay, right? But when I go for chlorine, why this happens? Any guesses, guys? Why do you think this is going to happen? Any guesses? Any guesses of why that when I put chlorine I'll get 50-50%, but not in case of bromine? Any guesses?
So does it have anything to do with its size?
Not size. Okay, the actual reason is it is going to be because of the reactivity, right? So when I compare the reactivity of chlorine gas, right, and I compare the reactivity of bromine gas, obviously we know chlorine is more reactive, right? Bromine is less reactive. So whenever you have high reactivities, right, there will be less selectivity. Again, I repeat, whenever you have high reactivities, you have less selectivity. That means the chlorine will not have time to look at in the sense that whether it's going to abstract the hydrogen from primary position or whether it's going to abstract hydrogen from secondary position. It really doesn't have time to do all that because it's very reactive, right? But since this reaction is pretty slow, right, now bromine has the time to make sure that only the most stable species is formed, and obviously I'm going to form the product accordingly. Okay, now the reason why this is happening is because chlorine is more reactive and less selective, and why this happens is because bromine is less reactive and more selective. That's how you should explain this particular phenomena which you're seeing here. Okay, right? So this is the first reaction which we saw, and this is the mechanism. These are the things which you have to know about it, right? Fine. Now, when I go for the next one, that is your allylic substitution, right? So allylic substitution, I go for a hydrocarbon. That is when I have an alkene when I put NBS, I'm going to get Br in the allyl position. Okay, right? Now, how are you going to deal with this? We'll see. Right? Okay. So let me go for the mechanism of this. Oops. Right. So what is going to happen? Right. So this NBS, right? So you don't have to worry about the structure. NBS is going to be, succinic acid, isn't it? So if you want, I can draw the structure. It's not a big deal. Am I drawing it correctly? Hopefully. So this is what is N-bromosuccinamide, right? Okay. So what is going to happen is this bond is going to, this is what is NBS, that's a famous one. Okay. So this bond will undergo actually homolytic cleavage to form, what is that? Free radical. That is Br dot is going to get formed from this, right? Br dot is going to get formed. Okay, right. Now we'll see when I go for the allyl group, that is CH3, double bond, CH double bond, CH2, right? So when this Br dot approaches, right? So right? So when this Br dot approaches, right? So what is going to happen, we'll see, right? So I have to get the bromine atom here in this position. That's what we are working on, right? 1 second, guys. How CH. Okay, so first it is going to abstract a proton, sorry, abstract a H dot. So I am going to have CH2 dot CH double bond CH2. Okay, right? And sorry, there is a dot here, right? There is a radical here, right? So when the abstract, one of the Br dot will be gone, HBr will be gone, right? And after that, what is going to happen? I'm going to get again Br dot, one more Br dot attacking here, right? So you can write plus H dot plus HBr if you want, you can write, right? And this is going to go, and again I'm going to get the position, I mean I'm going to get the substitution happening at this position. So again you will be getting the product accordingly. You will be getting something like this. Yeah, this would have been the product, right? So again, a very simple mechanism. You just have to understand that I'm going to have in the allylic substitution with respect to NPS, you are going to have an allyl radical which is getting formed. Okay, right? Now it's pretty simple, people. Now they see, I can even get the product here, right? Now, how is it possible to get the product here? It's pretty simple. Now, what happens is, assume that this pi bond which is here, is undergoing homolytic cleavage. Okay, now if this pi bond undergoes homolytic cleavage, right? So what is going to happen? I'll write it here, right? So I can have, so okay, now look at this, guys. Now see, if this happens, I'm going to get a free radical here, right? I'm going to get a free radical in this carbon, right? And I'm going to get a free radical in this carbon when I break this pi bond, right? So what is happening now? I have a free radical here. I have a free radical here. Now they both can come together to make a bond, right? So what will you see happening is something like this. I will have CH2 double bond CH2 dot. Yes, hope you understand how this came, right? So if this pi bond undergoes homolytic cleavage, I am going to form a radical here, and there's a radical here. Now they both will come together to make a bond here, and the radical is still left. The radical is still left in this third carbon atom. So you can have the product happening in the first carbon atom or the second carbon atom. Now you see that there's going to be little symmetric, so you don't see much difference. But if I give you a reaction like this, something like this, once again, right? Say if there is, okay, this is the position, right? Okay, now you can see there we can get a multiple of products. We say if I even put a CH3 here. Okay, now it makes some sense, right? Say now, what are the allyl positions I can get is the question now, right? So now this is the double bond, right? And this is the single bond. So here I can have one allylic position, right? Same way, this is the double bond, this is the single bond. So yeah, again here in this position, I can have Br dot coming, either of the places, again, allylic position, right? But I think this particular case will not happen because there's a CH3. Okay, guys, CH3 cannot come because I cannot abstract CH3, right? So yeah, just a H. Okay, so now again from the previous case, what you saw, right? I can have substitutions happening at different multiple positions, right? So if like assume that say this is the if I just take this position, right? If I just remove the H dot and I make a radical there, we'll see what happens. Right, so there is a radical here, there's a double bond here, there's a double bond here. Now, what can you see? So again, you can see that this particular double bond can undergo a homolytic cleavage, what you saw last time. So I can write this particular structure in this way, right? So now see, if I make the bond here, I can have an allyl, I mean a radical formed here, and there is a, wait, I'll just read out the diagram maybe little, yeah, better, right? So this I can undergo rearrangement. This is called as free radical rearrangement, guys, right? So you will see that, oh god, this is really not happening. Why is it like this? Okay, right? So you can see that there'll be a double bond here, right? And there would have been a radical formed here, right? And this double bond still stays, right? So again, this is another position where you can get the double bond, right? Now see, look at the product, guys. If this was the product, I would have directly got a BR here, right? If this was the product, I would have directly gotten BR here. Now there's a possibility of getting BR here also, because there's a radical getting formed. Again, what can happen? This double bond can undergo homolytic cleavage, right? So now if that's the case, what will happen? You will see that again, this dot and this dot, that is a dot here, and the dot this will combine together to make a bond, right? So now you will have a bond here, and there is a bond here, and where is the allyl? Where is the radical? This is the radical, right? So again, in this position also, you will be able to get the free radical. Okay. Now again, if you start from this position, right? I said that there are two allyl positions, right? So again, you can have it here. I think you can have it here. I think you can even have it here, right? So multiple places you will be able to have the allylic substitution based on the rearrangement which are possible when it comes to free radicals. Okay, so guys, did you understand what I'm trying to say? Right? NBS is going to give me a allylic substitution. That is okay. You can just find the allylic position and put it there. But if you didn't know the mechanism of this particular reaction, that is, if you don't know that I'm going to have free radical as the intermediate, right? So on there you can see how many different products I can get. But if you didn't know the mechanism, if you just know that it is going to be a allylic substitution, you will just say that I'm going to have here, I'm going to have here, and nowhere else. But you see how many possibilities I'm getting. Right? So yeah, this is fun. Knowing mechanism is always fun. It is going to give you a lot of insight about how the reactions, what are the different types of products which I'll be able to get, right? Okay, hope, is there any questions, guys? You want to ask me anything? Okay, so I suppose that you understood, right? Okay, I'll continue then. Right, now to the third reaction, guys. We spoke about the first free radical substitution in this CH2 in the presence of H2. Then we went for NBS, allylic substitution. Now we are going for anti-Markov-Nichols addition of a HBr, this one. Right, so we are going for anti-Markov-Nichols addition of HBr. Right, so when I put HBr alone, I'm going to have a different reaction, guys. Right, I'm going to have a carbocation as an intermediate, right? So here you're going to get free radical as the intermediate. That is what is going to happen, right? Now it's pretty simple, the mechanism. We'll see what happens, right? Okay, so basically you have a double bond, right? And you are putting this Br2 in the presence of H2O2. Again, guys, here I'm going to have chain initiation, chain propagation, chain termination steps, but I can just give you the gist of it. It's really pretty simple. Okay, so what is going to happen, we'll see. So this first, I have this H2O2, that's the catalyst here. So this, you can even use H2O2, or you can even use ROOR, in the sense that I should have a peroxide linkage. You hope you know what is a peroxide linkage. OO single bond linkage is what is called as a peroxide linkage. Okay, so either you can use H2O2, or you can go for any other organic peroxides. These are what are called as organic peroxides. Okay, fine. So this is going to be there. Now what is going to happen is this, okay, I'll just write H2O2 itself. Right, now this H2O2, this bond is little weak. Okay, so this can undergo homolytic cleavage, right? So this is going to come here, and this is going to move here, homolytic cleavage. So you will be producing 2OH dot. Okay, right? And this 2OH dot, oh, sorry, it's HBr, not Br2. Guys, I hope you, if you are listening, you have told me, right? This is not Br2, this is HBr. Right, okay. Now what is going to happen is this is going to combine with HBr, this OH dot, right? And it is going to abstract the H dot from this. So I'm going to have H2O plus Br dot getting formed. Okay, so first the H2O2 undergoes homolytic cleavage to form OH radical, hydroxy radical, right? And that is going to react with HBr to form your H2O, and that is abstracting a hydrogen and Br dot. Okay, now this Br dot is going to attack the alkene. Okay, so we'll see what happens there. Right, so this Br dot, which is getting here, right? So if this Br dot attacks, now it can attack only in two positions, right? So either this Br dot can attack this carbon, or say can attack this carbon. Right, now accordingly you have to make sure that whichever is more stable, whichever is going to be more stable and more stable. What is the intermediate again? If this Br1 undergoes, obviously this bond has to undergo homolytic cleavage, is it not? The pi bond has to undergo, for, like, let me put it like this, right? So first let me make the homolytic cleavage, right? So if I make the homolytic cleavage, like, it's actually not happening, guys, it's actually all simultaneous, but just for you to understand, I'm doing all this. Right, radical. So now you can see why is it that the Br dot can attack either this carbon or this carbon. You can understand why is it happening. Right, so when, say, if Br dot attacks this carbon only, what will be left with? I'm going to get a Br here, and there is a dot still left. Now what do you see? There is going to be a secondary free radical which is getting formed, right? But if the Br would have attacked here, I would have got a primary free radical, say something like this. Br is here, and there is a radical here, right? So obviously this is my primary free radical, this is a secondary free radical. So obviously we know secondary free radical is more stable than primary free radical. So what will the product be? So accordingly, now again the H dot will come and attack here, right? To this carbon, H dot will come and attack here. The abstracted H dot will come and attack here. It's pretty simple. So you will see that the major product is anti-Markovnikov's product, right? You will get the Br here only. If it was Markovnikov's product, this is where you would have got the Br. Okay, right? So this is here, and why the you would have studied 1,000 times, right? Anti-Markovnikov's addition, all these things, right? So it's pretty simple. Why is it happening? Is because you just have to undergo free radical addition. This is not substitution actually. Like, actually, I shouldn't have told you that it's going to be substitution. First two reactions are substitutions, yes. But this is an example for free radical addition. Br dot and your alkyl radical is going to undergo addition reaction. That's how it is going to be. Okay, now main thing what you have to understand here is, guys, when say I have sorry, right? So when I have this combined with right, So again, you expect anti-Markovnikov's product, but you are not going to see that. You are actually going to see this only. Cl coming here is what you will see, right? Now, what is the reason? Not only for this, if I go for HF or HCl in the presence of H2O2, right? Again, you're going to get only Markovnikov's product, right? So the anti-Markovnikov's product is possible only for HBr. Please make a note of it, right? Write a note beside this reaction and write, or this anti-Markovnikov's addition is possible only for HBr, right? Even if you put H2O2, when I add it with HCl, you are going to end up with your Markovnikov's product only. Okay, now what can be the reason for this is the next question which comes to your mind. So why is it that HCl is not giving me anti-Markovnikovs, but HBr is able to give, right? So if you look at the mechanism again, you'll be able to understand why that happens, right? So what you see here is that the first step, this undergoes homolytic cleavage, and I'm going to form hydroxy radical, and this reacts with HBr so easily. I'm going to form Br dot, right? But this particular step is not possible with HCl or HF. Why? Because HCl bond and HF bond are quite strong, that from that I cannot remove I cannot remove Cl dot or F dot from these two molecules. Only then obviously that is going to attack and all these things are going to happen, right? So the reason why HF and HCl is not capable of giving anti-Markovnikov's product is because the bond strength, the bond energy for HCl and HF is actually very high, right? So if I go still more depth and explain you, this particular step we have here is actually an exothermic step, in the sense that because of this, energy is going to get released, right? But if you're going to have this two making sure that this is happening, this will be an endothermic step, in the sense that I have to supply energy for this to happen, right? Only then the reaction proceeds. So that is why at room temperatures or at normal conditions, HCl and HF are incapable of giving Markovnikov's product. Even though if you put H2O2, you are going to get the Markovnikov's product only. Okay, right?
So for HI,
Fine.
will it work?
HI, yeah, definitely HI will not work, right? Okay, fine. Okay, fine. Now the reason is different, but right, HCl and HF will not undergo this reaction because they have high bond strength, right? Now, not only in this reaction, guys, even if I go for the first reaction, the alkyl substitution, CH3CH3 giving CH3CH2Cl, even in that reaction, if I put I2 bar H nu, Br2 bar H nu works, Cl2 bar H nu works, I2 doesn't work, right? Now, why I2 doesn't work is because I dot is highly unstable. You will not be able to isolate the iodine radical. So iodine radical, I don't think any reaction you can see that iodine radical is getting formed. Okay, so even though the bond is little very easy to break, right? Compared to the HBr bond, HI bond is easier to break, but still it doesn't give me Markovnikovs because I dot cannot be formed, in the sense that I dot is very unstable, right? Br dot is quite stable. Cl dot F dot. Okay, even if I talk about F dot in the first reaction, that is your free radical substitution, it is more reactive than fluorine, more reactive than chlorine also, right? So that reaction will be very violent. That's why we didn't see it. But again, that is not going to be of any practical importance to me, because a lot of mixtures of product I'm going to get, right? Because that fluorine is so fast that I'm not going to get one single particular product. Okay, right? So hope you understand why HI also doesn't give. It's because I dot is really unstable, right? Cool. So these are the three reactions where you will see free radicals getting formed. There are a lot of other reaction, guys. Like maybe if as I go through the course, maybe I will tell you. For now, this is what I remember: the important reactions, right? Okay, right? That is the free radical substitute. Actually, it's a combination of free radical substitution and free radical addition. So these three are the reactions. That is the first one, the second one with NBS, and the third one being anti-Markovnikovs. Right? Okay, fine. Now we'll move on. Right? If that is about the free radical. There are other types of reaction. We'll just look into it. Right? Fine. I'll just make a page. What is the time? Oh. Right. So next one, like maybe we'll just take it from this itself. I want to go for second class of reaction being, I can go for addition reactions. Okay, so I hope you understand what is an addition reaction. I see I need to have an unsaturated a bond, that is a double bond or triple bond, and to that double bond or triple bond, something it is going to get added. Say something like HBr addition to a double bond, HBr is getting added, right? But guys, please understand, I can have two types of addition reaction. One being nucleophilic addition, the other being electrophilic addition. Electrophilic, right? And nucleophilic. Okay, so what is the basic difference here? Now, please understand, guys. Say, I'll just give you a small, I have a double bond. Right? Say I have a C double bond C. Say I have a HBr or H2O or whatever it is you want to add. Okay. Right. So now we know what is going to happen. See, why do I call it electrophilic and why do I call it nucleophilic is because of the mechanism. Again, you have to know the mechanism to understand what is the difference between electrophilic and nucleophilic addition reaction. Right. Now, please understand here, I have a H plus. That is what is going to come. And I have a Br minus. So what you see here is that I am going to have an electrophile, which is having a positive charge, and I'm going to have a nucleophile, both of them getting added here to this C double bond C. And we know I'm going to get a H here, I'm going to get a Br here. That is very simple, right? Fine. Now, if I take a C double bond O, that is any carbonyl carbon, your aldehydes or ketones, anything you take. Now, say if I go for HCN addition, right? So again, what do you see here? You have a H plus, and here you have a Cn minus. You have electrophile, you have a nucleophile, right? But in this case, it is going to be called as an electrophilic addition, and in this case, it is going to be called as a nucleophilic addition. Why is it so? When I have a C double bond C or when I have a C double bond O, addition reaction contains both electrophile and the nucleophile, right? But when I have a C double bond C, I call it as electrophilic addition. But when I have C double bond O, it is going to be called as a nucleophilic addition. Now, what is the reason behind this, right? Any guesses, guys? Any guesses of why is it going to be called this way? Any guesses you wanna give me? Any guesses? You obviously guesses need not be right. Hmm.
Sir, in the second case, the
Hmm.
carbon's gonna get a positive charge, so it's nucleophilic addition reaction.
Okay, so if that's the case, you're gonna tell, say, if I add H plus to this, now this bond would have broken. I will be getting a positive charge here. Again, this bond breaks. I will be getting a positive charge here. So it's not about that. So guys, it is about which attacks first. Okay, so in your electrophilic addition, the electrophile attacks first, the H plus attacks first, right? And in the case of a nucleophilic addition, the nucleophile attacks first. That is the basic difference. Okay, so it depends on which attacks first. In case of an electrophilic addition, electrophile attacks first. In case of a nucleophilic addition, nucleophile attacks first. Very, very simple, right? Okay, now if you look at the mechanism, I think we'll just for now we'll talk about only electrophilic addition, guys, because nucleophilic addition will take up later when I go for aldehydes, ketones, and carboxylic acids. But I'm just letting you know that there are two types of addition reaction. Okay, so we are
Sir,
going to
is actually
concentrate.
knowing the order in which, like, which attacks will it actually be useful?
Yes, definitely, it is going to be useful. It is definitely useful, right? So why I say it's useful is that now if you see that this is going to happen, right? This is going to happen. I'm going to say no. Okay, this is going to happen. I'm going to have this bond broken. I'm going to have a O minus getting formed. All this as well will happen again. H plus will attack here. That is okay. But if I assume ulta, or say in this case, if I assume that Br dot is the one which is coming first, right? What will you see? Say, I'll just write it again, maybe if you understand. right? So when say Br dot, oh God, sorry, Br minus, not Br dot. Okay, so when Br minus attacks first, either of the carbon atom, say this attacks here and this will go here. Now, what will you see is that I am going to have a carbanion getting formed. Is it not? Because this already is a negative charge, that was it goes attacks this carbon and this bond breaks heterolytically to form a carbanion, right? But my experiments, there are experiments to prove that carbocation is the intermediate. There is a way that I will be even able to isolate a carbocation and study about it. Again, obviously, when I go for higher levels of chemistry, right? So the experiments proves that it is not a carbon, it is actually a carbocation in this particular reaction, which is the intermediate, right? So if you say that this is the one, if I mess up with the what to say, who comes first and who comes next, you will entirely change the intermediate itself, right? So please remember that that the what is it, who comes first and who comes second actually matters, because if you mess up with it, the entire what is that, the intermediate itself is changing, the entire mechanism itself is changing, like you will not be able to explain the product formation properly. Okay, right. Fine. So we will concentrate on this electrophilic addition a little more, right? And yeah, okay, fine. So first one in this electrophilic addition, I'm just talking about alkenes only, people, right? Because we're just concentrating on that, right? Say, I can have addition of so many things, right? Say first I take addition of HX, right, to the double bond. We just saw that what is going to happen. So I'm going to have a C double bond C, and I'm going to have a HX like HCl or HBr. Now I can have addition of H plus and Br minus. Okay. Now what you really need to understand here is the intermediate, right? So I just showed you how the intermediate is getting formed. I'll show you one more time, right? So if first the H plus comes, okay. Now when this say, like before that itself, I can see generally electrons are the one which will attack the electrophiles, right? I mean, the nucleophiles are the one which will attack the electrophiles, not the other way around. It's not, you should not say that H plus comes and attacks here, right? I should say that this pi bond goes and attacks this H plus, something like that. That's how we should speak. But again, like that much details really not required, right? So now depends on which carbon is which carbon is losing the bond. That means, say if this carbon is attaching with H plus, right, this carbon is losing the bond, and if this H plus goes to this carbon atom, this is the carbon atom which is losing the bond, and accordingly I'll have a positive charge. Okay, so you will see that I am going to have this carbon losing the bond, so it's going to form a carbocation, and the H came here. Okay, pretty simple. So what you have to understand is here carbocation is the intermediate. Okay, right? And based on this only you have the Markov-Nichols rule, right? Say now the same thing. If I take and if I put just HBr and nothing else, so you see that the carbocation is obviously going to get formed here, right? So obviously the Br minus will come in and attack the now positive charge wherever is the positive charge. So you will see that the product is here, right? This is the major product, because now last time when you saw anti-Markov-Nichols addition, that the mechanism was entirely different, guys. So here the mechanism is different. Here the carbocation is the intermediate. So you will see this is the major product. The minor product is obviously when I have the Br atom coming here, right? Okay, now there is one most important thing I have to teach you. Not most important thing. This is a very relevant thing which you have to know, right? Now let me actually little create some amusement in you, right? Okay.
Sir,
Now, yeah.
sir, why is it that the carbon with like the lesser amount of hydrogens, like why is it considered that the bond is moving? I mean, the positive charge is going towards that.
Oh, so basically in chemistry, what we generally do is, even though we have protons and electrons, what we assume is electrons are the one which is actually moving inside the atom, right? So this is not going to be much of a detail. Like you can even say that this, I mean, sorry, you can even say that this comes and attacks here. It doesn't matter. Like it really doesn't matter. But generally, well, like the conventions which are used in chemistry says that electrons are the one which is going to move. The positive charges will generally not move. That's the thing. But again, it is not going to be much of a deal. You don't have to worry about it. Okay, right?
No,
So
sir, but just by mistake, if I put like the positive charge on the other side, like on the terminal carbon, then the whole the product will completely change.
that's what, like you see, either you do this, either you make the pi bond attack or you make the electrophile come and attack. The carbocation formed is going to be same only, as long as it is symmetrical. Now in this case it is symmetrical. Say now you can have the carbocation here also, right? But again, that comes with practice. Say for example, let me give you this case, right? um, right right um, say if I have a double bond here, right? So you easily know that you have to form a carbocation here, correct? Right? So now how will you have, say H plus comes, right? Now you don't have to worry about the where exactly which carbon atom is the, how do you do it? It's just go for the more stable carbocation, as simple as that, right? So now if I form the carbocation here, this is going to be a secondary carbocation. If I form the carbocation here, now that is going to be a tertiary carbocation. So obviously you will see that I am going to have carbocation here in this carbon atom, right? That's how it is. It's all about the more stable carbocation. That's it, right? So anyways, like that's what it, that's now in this is this the question you asked? Are you do you understand?
Ah, yes, sir, yes. Oh, it's the
Okay,
carbocation stability, sorry.
yeah, exactly. So it is just going to be based on the carbocation stability. Now if it is symmetrical, no issues, you can have either of the carbon atom to have the positive charge. But if it is not, then obviously now in this case also, right? In this case also, what happens, you will see that this is secondary carbocation, more stable. This is a primary carbocation, less stable. So obviously that is going to get formed. Okay, right, fine. So
Yes.
let me now let me little amuse you. Okay, now say if I have, say I have mm, say the double bond is here. Okay, right? And say there is a CH3 here. Okay, right. Now if I put HBr or any other water or whatever it is, right? So when I put this, okay, so what will you see happening is the double bond is gone, obviously. So you will have the methyl group and you will have the Br attached in this carbon atom out of nowhere. Okay, now what is happening? We really have to understand. Okay, guys, have you studied about this? Okay, I hope not. Definitely. Right, fine. So we are going to study a new concept now. What is the time? Okay, half an hour we have, right? So we are going to study a new concept now, right? So I'm going to take you through that. Right. So we are going to study rearrangement in carbocations. That is what we are going to study, right? So what I'm trying to tell you is that if there is a possibility, right? If there is a possibility that there's a carbo, okay, I assume that there's a carbocation, okay, and that carbocation is not so stable, assuming, right? And if there is a possibility that that particular species, that particular carbocation can rearrange itself to form a more stable carbocation. Again, I repeat, there's a carbocation, little unstable, right? Now, if there is a possibility that that carbocation can undergo some kind of rearrangement to form a more stable carbocation, that rearrangement will definitely take place. Okay, that's what you understand. So why is it that the rearrangement is happening? If someone asks you, is because the rearrangement is happening because I am going to form a more stable carbocation. Okay, Right. So we'll take like fine. Now, what are all the things which you can do? Like if you want to make a more stable carbocation, right? What are all the types of rearrangement and what are all the rules which you have to follow, right? Okay. Now the first rule or the first type of rearrangement I can have is what is called as your hydride shift. Okay, right? H minus is going to shift. Right. Now let me take an I think that this is the best example. The example which I took here is an example for hydride shift. Okay, we'll see what happens there. Right. So maybe I think if I write say it will be CH2, CH3, CH2, CH, CH3, CH, double bond, CH2. Okay, right. So now obviously the carbocation, I think I can make some space. Right. So if I look at this, obviously the more when I first put, oh, I'm sorry guys. Right. So when I first put the H plus, right, I know what is going to happen. This H plus is going to attack here only. So obviously I'm going to form a secondary carbocation, right? So if I write that out, I will be getting CH3, CH2, CH, CH3, CH plus CH2, right? I'm sorry, CH3. Yeah, the H plus has been added. So this is CH3. Okay, so this is the secondary carbocation, right? Now, what can happen is you can have a hydride shift. Now, please understand, guys, there are going to be three types of shifts: hydride shifts, alkyl shift, and ring expansion. Like I'll tell you all the three of them, but don't worry. But whatever you're gonna do, right? Whatever you are gonna do, you are going to shift the species only from the alpha position. In the sense that there is a carbocation, there is a carbon having the carbocation, you can take the H minus or you can take the R minus or you can go for ring expansion only from the adjacent carbocation which is adjacent to the carbon atom which is having the charge. In the sense that either you can have something happening from this side, this carbon atom, or you can have something happening from this side. Okay, you cannot shift the hydrogen from these two carbon atoms, no, or you cannot shift the hydrogen from this carbon atom. You just you can shift the hydrogen or the alkyl group only from the next carbon atom, either this or this, right? But again, which side it is going to happen again depends on which side. If I do, I can form a more stable carbocation. Okay, so if this if this side comes, like I'll tell you what exactly is happening, but if this side is the one which is involving, I am going to get a primary carbocation. But if this carbon involves, right, I can have a tertiary carbocation getting formed, right? You must always go for more stable species. If there is no possibility of forming a more stable species, there is no question of rearrangement, guys. Please remember that. Okay, if there is no question of forming a more stable carbocation, there is really not a question of rearrangement happening, right? But in this case there is some scope, so it will take it, the molecule will rearrange to form a more stable carbocation. A secondary carbocation is going to get converted into a tertiary carbocation. Okay, so we'll see what exactly happens, guys, right? It's pretty simple, right? So from this itself I'll take, right, say now instead of this hydrogen writing like this, right, let me write the hydrogen like this. Okay, so we're talking about hydride shift, right? So hydride means I'm going to have H minus. So this hydrogen along with the bond pair, you will see there are two electrons here, one electron, another electron, right? So there are two electrons here. So the H along with the electron goes and attacks this carbon atom, right? So H minus, carbon plus, it is neutralized, but this carbon has lost electron. So obviously you will see that I'm going to have CH3, CH2, C. Now there is a hydrogen loss, so the plus will come, CH3, CH2, CH3. Okay, so this is the carbocation getting formed. And obviously now you can understand why the product is forming as such. Where is the product? Here, right? So look at the products. You see there's a double bond here, right? But where will you see, where are you seeing? Here is where it is coming, because due to rearrangement, right, the carbocation is formed here, and the Br minus will obviously come and attack only the positive charge. It is going to come and attack here, and accordingly the product is going to get formed. Okay, fine. This is what is called as hydrate shift. Again, again I repeat, you can do the hydrate shift only from the next carbon atom to the carbon atom which is having the positive charge. Okay, right? I can even have hydrate shift, say if it's something like this. Maybe I have to show you some other example. What example I can show you? Say something like this. Say I can have a ring structure. Say this is a fine member. There's a methyl group and there is a hydrogen here. Okay, right. So again, when the bond breaks, right, when this pi bond breaks, now I can say that I'm going to have this kind of carbocation getting formed. Right. Say now the carbocation is here. Right. Say assume that there is a hydrogen added to this, new hydrogen, which was added to this. Right. So now what can happen? I have a H and a CH3. So again, this is the carbon atom, and the next carbon atom is again having a hydrogen, right? So this H minus can shift, right? Can shift to this, right? Now what will happen? You will see that, okay, let me make some space, right? So this is the carbocation. So if I have the rearrangement happening, so you will see that I am going to have a carbocation, right? Carbocation here, and the hydrogen has actually gone here, right? So this hydrogen, if I just mark it, if I just put an asterisk mark, this hydrogen has actually come to this position. Okay, so again, what do you see? The secondary carbocation is getting transformed into a tertiary carbocation, right? So again, this is an example for hydrate shift. Okay, fine. So now we'll move on. Guys, you have to practice a lot. This is the first time you're looking at it, and I can have directly problems asked from this, right? So anyways, don't worry, we'll do a lot of practice. Don't worry. But the first thing is you have to understand why this happens, how this happens. All these things should be clear. Okay, fine. Fine. So that's about your hydrate shift. Now we'll move on to your second type of shift, is my alkyl shift, or I would say it's my R minus shift. It's like H minus, I can have R minus, but this R minus 99% of times will be CH3 minus only. You don't have to worry about other groups because they're very bulky to undergo. The hydrogen can easily undergo because it's little small. It's one of the smallest species I can have. Again, CH3 is compared like little bigger, but again smaller compared to other bigger species. So only CH3 minus or say H minus can only undergo the shift. Okay, fine. So let me give you a case. Right. If we take an example, right? So the example now I can take would be, okay. Now there are two methyl groups. Assume that, right? And say the carbocation is this. Now, last time what you did, guys, last time from this is the carbon atom, right? So from this carbon atom, I shifted a hydrogen, right? Because I had a hydrogen here. So I went for hydrate shift. Now, in this case, these both are CH3s, right? Now, this is also CH3. This is also CH3, right? So you can have the shift happening. Well, I mean, shift of CH3 minus happening. So CH3 minus can come and attack this carbon atom now, right? So you will see the product again. You will see an amazing difference in the product if you what you expect and what you're really seeing, right? Okay, now I have a methyl group here and I have a methyl group here, and obviously the positive charge is on this carbon atom. So again, what do you see? A secondary carbocation is getting converted into a primary carbocation. Yes, right. So again, this is an example for alkyl shift. Now in the previous example, what I took in this example, again, instead of hydrogen, I can put a CH3. Again, I can make sure that goes there. Again, I can have a methyl group coming here and I form a carbocation here. Again, that is an example for alkyl shift. Okay, basically CH3 minus shift is what you have to know. Okay, right. Now, last thing, right? So, guys, any question regarding hydride shift and alkyl shift? So, please remember, whenever you know that there is going to be a carbocation as the intermediate, right? Please check for a rearrangement. If you're not going to do that, if you're just going to write what you are expecting, -1 in your JEE mains exam, that's how it's going to be, right? So, please make sure that. Okay, now answer this question. I have. Say this carbocation with me, right? Is there any possibility that this carbocation can undergo rearrangement? Tell me.
No, sir.
No. Why?
Because there's no possibility of forming a more stable carbocation.
Absolutely true, right? So this is a secondary carbocation. Say if you shift hydrogen atom from this, you're going to form a primary, and again if you shift hydrogen atom from this, again you're going to form a secondary carbocation only, right? So hope you understand where to check, how to check. Again, it will come with practice, do not worry, but the overall idea must be very clear, right? Fine. Now that you understand these two, now we can move on to the last type of shift, a last type
Sir,
of rearrangement. Yeah.
sir, I have a doubt in the previous
Hmm.
example.
Yes, Kana, tell
Uh,
me.
the previous one, sir.
Oh, this one. Okay, here. Ah,
Like the first one, sir. Actually,
okay. This one.
yeah. So here we can also do the
Yeah.
alkyl shift,
Hmm.
no, sir.
Good. Okay, we'll do that. We'll see what happens. Right. So if instead of this hydrogen, you're telling we'll. Oh, sorry. Instead of this hydrogen, you're telling this alkyl group can be shifted.
Yes, sir.
Is that what? Okay. Now we'll see what happens there if this shifts here. Okay. So this is how the product is going to be. CH3. Sorry, guys. 1 second. Oh, wait. CH3, CH2. Now I have a CH, right? The alkyl group is gone, right? So now I'll get a carbocation here, right? Now what happened to the next one? CH3 will come here and CH3 will come here. Now what happened here? Now if you shift your CH3 to this, what is happening? Secondary carbocation, again a secondary carbocation only because the CH3 are shifted here, right? But if you shift hydrogen, as I told you, then you can end up with the tertiary carbocation. Look at the difference between this and this, right? So the basic
Mm.
difference is this, right? This is a tertiary
Yeah.
when you go for hydrogen shift, but when I go for alkyl shift, you still have only a secondary carbocation.
Yes,
Understood,
sir. Got it. So,
right?
so if there's a hydrogen present, then hydrogen like hydride shift gets the more priority.
Not necessarily. It is not about which gets the priority. It's about in which way you can form a more stable carbocation. That's the question, right? Maybe if I can just complicate a question, right? Let me complicate a question. Everybody can answer this question actually, right? So let me make a question in my mind first. Okay, but fine. Let me try. Oh God. So let me take a cyclobutyl ring. Right, say there is a double bond, or like I can directly put as a CH2. This is really irritating. 1 second, guys. I have to make this work somehow. I don't know what I'm doing wrong. Okay, so if this is the carbocation, there is, I think, only one way that I can do something. There is I have to form a primary. Just guys, I don't think this would work. Right, just give me some time. Just give me 1 minute. I will just come with an example. Okay. There is a hydrogen here, right? Okay. Will this work? I have. If the CH3 goes this side, can have no. Okay. Why am I doing so much? Let me put this also has a hydrogen. C2H5. Oops. Where is there any undo button? Okay, thank you. Right. If I, so this hydrogen, there is a positive charge here. Okay, so let me take this example, people, right? So now you can have shift happening from both sides, right? In the sense that this hydrogen can shift, hydride shift can happen, right? Or say any one of these methyl groups, right? Again, can go and attack this carbon, like the carbocation. Okay, so we'll just see what are the possibilities. Okay, say now now this ethyl group still stays C2H5, and say I'll just talk about the hydride shift now. So we'll just see I have a CH3, another CH3, and the CH3 was here. Okay, the CH3 is here, and the carbocation would have been here now, right? So this is one of the carbocation possibilities when I go for hydride shift, right? So now when I go for methyl shift, now we'll see what happens. I will have, this is still the C2H5, right? And say one of the methyl group has gone to this carbon atom, and this carbon atom already has a methyl group, and say there is one more methyl group in this, right? And obviously this carbon is going to have the positive charge. No issues, right? So both are tertiary carbocations, right? This is a tertiary carbocation, this is a tertiary carbocation, but I have to see which is more stable. And I think you have all the tools in your backpack to decide which is going to be more stable, right? You can use hyperconjugation for this, right? So if I use hyperconjugation, I can write this as CH2. Let me make some space. This is CH2, CH3. Okay, right? So now how many hyperconjugating structures it can have? We'll just look into it. So there are two alpha hydrogens. Here there is CH3, so there is 3 plus 2, 5. And I think this carbon atom has a hydrogen here, right? Isn't it? 1, 2, 3, 4. Yeah, there is a hydrogen atom here. So totally 1, 2, 3, 4, 5, 6 hyperconjugating structures for this particular carbocation, right? Say now if I go for this one, we'll just check how many are there, right? Say now this has 3 and this has two more hydrogens, right? And this also has 2 hydrogens, right? So totally how much? 3 plus 2 is 5, 5 plus 2 is 7. What is that? Hyperconjugating structure. So definitely if the rearrangement happens, the rearrangement will take place like this only, because this forms a more stable carbocation. Okay, so now one side you did hydrate shift, the other side you did methyl shift. You got two different carbocations. Both are tertiary, right? But again, now answering a question, sir, how should I decide? It is purely based on your stability of carbocation, not based on whether I can shift hydrogen or whether I can shift CH3. It's not based on that. It's based on the stability of the carbocation. Is it okay? Right? So I think everybody would have gotten a very good picture from this, right? You can shift whatever you want, but please make sure that you are going to form the most stable species out of the rearrangement. That's the most important point. Okay, right? What is the time, guys? Yeah, 5 more minutes. I think I will not be able to start ring expansion. It's okay, right? So ring expansion, maybe next week I will start. Okay. Fine. Any doubts, guys? Any doubts? I think today you learned a lot of stuff, a lot of new stuff regarding organic, right? I think I was of some help, because now you'll be able to appreciate more and more reactions you see. You don't have to mug up the reactions. You don't have to mug up the products, especially, right? Now, not only for this, we will see mechanism for all the possible reaction, but there are certain mechanisms where I will tell you that say this is really not required because it's very complex, and with the help of mechanism you are actually not going to gain anything, right? There are certain reactions like that, but for 90% of the reactions, right, I will take you through the mechanism. Don't worry. Okay, fine. Any questions, guys? Any questions you want to ask? Right. Okay, so I hope there are no questions, right? Fine, guys, we'll meet next week again, right? Thank you so much.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah, understand the session.